Okay, so I'll start just by explaining how this is going to work. It's basically, this is part one of three. At the same time tomorrow and then on Wednesday I will do parts 2 and 3. So today we'll just see what are deep neural networks. I'll give a bit of history and then also show you what they are. Tomorrow we'll look at how we train deep neural networks with data. We'll also talk about some regularization techniques and other practical considerations. And then I think there was also a request from a few of the other speakers to also just talk about or introduce convolutional neural networks. So that's a special type of neural networks that is used a lot in computer vision. Okay, so that's more or less the plan. So one way that we can think of machine learning or a certain class of models that we use in machine learning is simply approximating a function that takes some input vector x to an output vector y. The idea with machine learning is then to use the data that we have to learn the parameters of that model so that it can then be applied to any input to produce a sensible output. So just as an example, a few examples. As input, we might have a history of stock prices, and we want our model to take that history and perform mathematical operations on it and then predict what the stock price will be tomorrow. Or we might have as input a set of pixels, and we want as output some sort of label that tells us what is going on in that image. This is the classic image classification problem. We might have a self-driving car that takes as input feed from a camera, and in this case it sees that there are people walking across the street, so maybe the model should output an action that says stop or apply the brakes. Okay. So machine learning models can be thought of as function approximators that map some input to output, and this is also a useful way of thinking about neural networks. Of course, as many of you would have seen, some interesting things are coming out nowadays where you can, if you train the model properly using a lot of data, you can input a text prompt, an astronaut riding a horse on Mars, and then the model is able to produce this image as an output, which is very impressive. Okay. And of course, with deep learning, this model, that box in the middle, would be a neural network. Okay. Now, as I say, we can think of the inputs as vectors. The outputs are typically also vectors or single numbers. So maybe I'll think of the input as d-dimensional vectors, just of numbers. When we are in the supervised learning setting, then we would have labels associated with all the inputs. We call them targets or responses or annotations. The idea with machine learning really is to learn that model from the training data that we give it so that it will generalize, in other words, map inputs that it hasn't seen during training to sensible outputs. Again, we might think of the model as a function that takes vectors in some d-dimensional space to, that example just takes them to a single real number, but it can also be a vector as output. A simple example of that would be this linear function that I show in blue, just a weighted sum of the input values plus a bias, and then we would have those parameters W and B that are unknown that we can learn from our training data. Okay. Our model can also be a probability distribution, so not a function that just maps a vector to a vector. And in that case, it can do things like describe a distribution over possible functions or give us some sort of uncertainty in the predictions. So again, just to illustrate this, we can think of our inputs now as a one-dimensional x value that's on the horizontal axis, and for every training example, those are the blue dots. We have a corresponding output, which is on the vertical axis, the y. So in that case, we have 5 training examples, and from those we want to fit a model and use the model to predict what should be the y value at that x of, I think that's 60, that dashed line. So once we've trained the model, we might end up with a straight line like that. I don't know if that's a good model, but anyways, there it is. And then we can read off the corresponding output at any input. Okay. So that is what we would refer to as prediction. We use the model to predict what is the y corresponding to an x equals 60. If we have a probabilistic model, we would call that prediction inference. So in the figure on the right, instead of a single value, we might now have a distribution of possible values corresponding to the input x. As that example shows, it's quite likely that the x is around here, but it could also be around here or around here. That the output is there. It's quite unlikely that it is down here. Okay, and that is obviously quite useful in many applications. Training, of course, then amounts to estimating the parameters of the model. So this would be that vector W of weights and maybe the bias. And as I say, we use training data for that. So that's the blue dots. If we have a different set of blue dots over here, we might end up with a different model or a different line over there. Okay. And tomorrow, when we talk about training, we'll talk about things like empirical risk minimization and perhaps also the principle of maximum likelihood. Okay. In this example, we chose a straight line and we tried to find the best line that fits this training data. We could have chosen a different model, maybe a parabola or some other mathematical function. So the process of deciding what the model will be is what we call model selection, and then picking appropriate structure for the model would be what we call hyperparameter tuning, and I think tomorrow I'll also say a few things about that, specifically for deep neural networks. Okay, so now just to borrow a bit of history from computer vision. As McElary said, I've done some work in that for a while now. And usually, I should say long ago, when I was a PhD student, it was common to do something like image classification in 2 stages, where you would first convert the input image into what we call a feature vector, and then train a model that can map the feature vector to labels. The reasons for that was that first of all, these images are it's usually very high in dimensions. The number of pixels can be quite high, and for computational complexity reasons, it made sense to first map the image to a lower dimensional feature vector before we then train a model on those. And the view also in computer vision was that we can use our human intelligence to engineer good feature vectors that somehow capture the things that are important for this problem. So pixels that belong to the background are not important if I want to determine what is in this image. So that's this idea of intra-class similarity and inter-class dissimilarity. And of course, as you would know, this step is very important. We want to be able to capture all those things well in our feature vector. Otherwise, we don't really have any chance of doing a good classification on that. And as I'm sure many of you also know, this is kind of the old way of doing things. The new way is just to try and learn the process of feature representation and classification jointly, or end-to-end, as we also say. And this is really the idea where deep learning started making a name for itself, is its ability to learn this feature representation together with the classification model. So instead of handcrafting a process that takes us from the image to a good feature vector for classification, we now just give the model the image data as input and ask it to do everything with that. Okay. So that's kind of where, to give you some sort of motivation for why deep learning is useful. I will now just quickly give a brief history of this. So I guess it started around 1958 when Rosenblatt introduced what he called the perceptron, which was an electronic device that could be used to learn basically a mapping from some input to output. Then about a decade later, Minsky and Papert showed that the perceptron was not able to learn very simple nonlinear functions. I think they used the XOR function as an example. I'll talk about what a perceptron is and how it relates to what a neural network is. But in the 80s, then people like LeCun and Rimmelhart found ways to train multi-layer perceptrons through backpropagation. And then, as you might know, there was, I think they call this the winter of artificial intelligence, when these neural networks received a lot of criticism. People were not too excited about them. The fear was this sort of black box nature of them. If you have a model that can learn anything and you don't really have control over what it is actually learning, it's hard to prove that it's actually doing what it's supposed to be doing. And then it was much later when I think also the power of computers caught up, that people like Hinton and Bengio devised tricks to practically and reliably train neural networks with many layers. So this idea of deep multi-layer neural networks. And then it was another few years until people started getting really good results with these deep neural networks. So there were breakthroughs in automatic speech recognition in the early 2010s. There were, of course, as you might know, breakthroughs in image recognition using AlexNet, that's the first paper there, and then ResNet, which were able to scale these networks to many, many layers. And those breakthroughs were so significant that people couldn't not pay attention to it. It just completely outperformed any of the best models that were available at the time. And people working in these fields, speech recognition, image recognition, were then very quick to start adopting deep neural networks. Then in the around 2013, 2016, there were also breakthroughs in deep reinforcement learning. So this is reinforcement learning using deep neural networks, again, as function approximators to map states to actions. This first paper was, as you might know, the paper on teaching a machine how to play Atari games, and this one by David Silver and his collaborators was on the AlphaGo system. Okay, and as I say, these breakthroughs were so significant that it seemed like almost overnight. It took over all these fields, and as I say here, it basically overturned just about every domain of modern data science. And then just maybe a quote from Jan Daufen, who said that, of course, deep learning is a useful tool, but it is not yet a solution to artificial intelligence. Again, I think we can think of this as simply as function approximators. Artificial intelligence, of course, would require a bit more. Okay, so now just to kind of go over what these models actually are. So perceptron, there's the picture, but basically in mathematics it is a simple linear transformation of an input vector x. So we multiply it with a weight vector w, or we take a dot product and add what we call a bias b, and then apply the sign function to that. And this gives us an output single value. If we apply the sign function, I guess this value can be plus or minus 1. And this is the picture. So we have, in this case, an input vector with 3 elements. There's our input nodes. Each one of these will be multiplied by a weight, W1 to W3, and then summed. So it's X1 times W1 plus X2 times W2 plus X3 times W3. That's what's happening here. And then we also add this additional number B in there. And then we apply the sine function over there, and that outputs the Y. Okay. The reason, of course, we add this bias is because we want this model to be slightly more general than one that would always map x equals 0 to y equals 0. Okay. You also often see that people, instead of having this little bias extra in here, we just have an additional input that always has the value of 1, and we multiply 1 with the weight that is there, which is the same as adding a term equal to that weight. So then we can simply write the model like this. It's a weight vector transpose times input x, where input x is now our original input with this extra element of a 1 over there. Okay. And if we don't only want one number as an output, maybe we want to map a vector to another vector, we can then simply stack these perceptrons, more than one perceptron like this, taking the same input into 3 different perceptrons, and then we have 3 outputs over here, and this is what we then call a layer in our neural network. Okay. And of course, if we multiply the same vector by different weight vectors, we can also write that as a single matrix multiplication. So the W would have the different weight vectors as rows, I guess. X is a column vector input, and Wx then gives us a vector output. Again, I can apply the sine function to each element of that vector, and that gives me my output vector. Okay. Oh, I think I skipped this point. The idea, of course, will be to, again, learn the weights, maybe this weight matrix W from training data. So this would be example inputs and outputs. So if X has these values, Y should have those values. If X has these values, Y should have those values. Lots of those examples would then allow us to learn what is the best set of weights for this layer. And we can now introduce depth into our network. So this is where we get our deep neural network, is by feeding the outputs of one layer into another layer. So we have our inputs over here. They map to outputs over there. These outputs then become the inputs for the next layer. Every time we just have this bias term as well. And in this case, we have, I guess, 3 layers, and that gives us our final output like this. And that is basically what a neural network is. All the other ones that we'll talk about might be just special cases of this one. Okay. We call this a neural network, or an artificial neural network, or a deep neural network if it has sufficiently many layers, or a multi-layer perceptron, MLP. This one is fully connected, so each of the outputs of a layer are connected to all the inputs of that layer. We also call it feed forward because the data always flows in one direction from input to output. And again, from input-output examples, our training data, we will want to learn optimal weights for all these connections in the network. Okay. So that's basically what a neural network is. As I've mentioned, at every perceptron, so at every node in the network, we would have the sine function applied to the output. The output is basically the weighted sum of the inputs, and we apply the sine function. If we do not apply the sine function, we would essentially have just a bunch of linear functions, a matrix times the vector, and then another matrix times that output, and then another matrix. So it's just a chain of linear functions, which mathematically would be equivalent to a single linear function. So by adding depth to the network, we're not actually adding expressivity. that's why we have that activation function. The sign function was used originally in a perceptron, but it's not really used in practice today. There are a few reasons for this. The sign function is quite sensitive to small perturbations. So if your input or the output is around 0, if it's just a little bit to this side of 0, the sign function will output 1. If it's a little bit to that side, the output of the sign function would be -1. The sign function is also not differentiable. There's a discontinuity at 0, which is not good for gradient-based optimization. The sign function's derivative, of course, is also 0 everywhere except at 0, so that's also not very useful. There are a few alternatives that people have started using instead of the sign function. So at every node in the neural network, you calculate a weighted sum of its inputs and then apply one of these activation functions, sigmoid or a hyperbolic tangent. ReLU, of course, has been very popular, especially in computer vision, and then there's a few others as well. So it's again a nice way to introduce a bit of non-linearity into the neural network, which allows us to model complicated functions better. Usually when we do something like classification with our neural network, as a final output, we might want the numbers or the vector that we get at the last layer to be positive numbers that sum to 1, so that we can interpret them as a kind of a probability distribution. So if I have an image classification network and I give as input an image and as output I want probabilities over the various classes, it might make sense for my output to have this property. And the one way we can accomplish this is through what we call the softmax function. It raises the outputs, or I should say it applies the exponential function to the outputs. That makes all of them positive, and then it normalizes by the sum of those so that they all sum to 1. That is the softmax, and again, this is useful for classification. We'll come back to this tomorrow as well. And then if we have positive numbers that sum to 1, we can think of the outputs as a kind of posterior probability of the different classes conditioned on the input. And as we'll see when we start training these neural networks, it will be useful to compare the network output to the expected output. In the case of classification, if we want to compare our softmax output, it's a vector of positive numbers that sum to 1. If we want to compare that to our annotated training labels, we could use this idea of one-hot encoding by basically creating ideal vectors as outputs where everything is 0 except the true label is a 1. Then there's some theory about why neural networks work so well. One of them is the universal approximation theorem that basically says that even if you have only one hidden layer, you can, in theory, represent any continuous function to an arbitrary degree of precision. In practice, it turns out that such a layer may need to be very, very large, so many, many nodes. So instead of, even though in theory a network with one layer can be very powerful, in practice, if we want to train these neural networks, it usually makes more sense to have multiple layers that are not as wide. So adding layers also gives us a way of increasing complexity, but keep the total number of neurons relatively low. And there's also some recent work now on similar kinds of theorems that say networks with arbitrary depth also have this property of being able to represent basically any continuous function to any degree of precision. So the point of this is just basically that neural networks are things that are built up out of very simple perceptrons, if we have enough of them structured in many layers, so we create depth in our network, we are really able to express very, very complicated functions, and we can learn them as well from data. The one thing that you may be thinking of is that let me just quickly go back to one of these pictures. If you look at a picture like this, of course this is a very small example. If I have as input the pixels of an image, I would have thousands and thousands of dimensions in the input. They then map to a hidden layer, and if I have a fully connected neural network, I would need weights or trainable parameters between every node in my input and every node in the next layer. So you can imagine that the number of parameters in this network grow very quickly. If I have 1,000 dimensional input and 1,000 nodes in the second layer, that's already 1 million, with the bias, I guess, learnable weights. So these neural networks tend to have many, many, many parameters. It's common nowadays to see models, neural network models, with millions or even billions of parameters. And that would be something that we call a model that is over-parameterized. It has far more parameters than is probably necessary, far more parameters than the number of data samples that we have to train on. And what that usually means is that if I try to train a model like that, which has orders of magnitude more parameters than data samples, the model will very quickly overfit. And as we'll also see tomorrow, there are ways of avoiding that kind of overfitting, specifically in neural networks. And the answer to this is, of course, firstly, we do need quite a lot of data typically, and the other thing is that we do need quite strong regularization. But yeah, we'll talk about that tomorrow. Then, oh, McGallery, we're going through this very quickly, so I don't know if anybody's going to complain. I wanted to end actually now just on, I thought there would be more questions, but anyways. Just a little bit of code. If you're kind of new to neural networks and you want to get started, there's a nice package called Keras, which is built on TensorFlow. There are other ones as well that are all equally nice. This is just a little example to show you how easy it is nowadays to build neural networks using these packages. Here I just have a very simple model. I use the sequential function from Keras, so it's just basically a feed-forward neural network. I create one dense layer. Dense is a different word to fully connected. It will have an input dimension of 4, and it will have 5 neurons, essentially. So it's going to map my input 4-dimensional vector to 5 neurons, and I set the activation function to ReLU. Then after that, I will have another dense layer, which will have, obviously, the number of inputs will depend on the outputs of the previous one, which is 5. This one will also have 5 outputs. And then finally, I will have my output layer, which will have 3 neurons. So my output will be dimension 3. And I guess this model is supposed to do classification, so I end with a softmax activation. So since there is a little bit of time, maybe I can ask you to do a little pen and paper exercise and see if you can calculate how many trainable parameters would there be in this network. Okay, I'll give you 3 minutes. So there would be 4 inputs plus the bias that I multiply by 5 in the first layer. Then I have as input 5 plus the 1 bias multiplied by 5 for the second one. And then 5 plus the bias times 3 for the last one. And that's 73. Okay.
Why is it a bias per layer and not a bias per node?
it is a bias per output node of the layer. So that is why I do multiply 4 by 5 and 1 by 5. Yeah. Okay, so that's it really for today. I don't know if you're welcome to ask any questions. Yeah. Like model selection, you mean? Yeah. No. So this is for some bizarre, for no particular reason, I decided that this model will have a lot of freedom in how many layers do you want between the input and the output, how many nodes do you want per layer, what should the activation functions be. There's loads of other things that you can also choose, and those we can think of those as I guess hyperparameters, and there are various different ways of picking good hyperparameters. Cross-validation is one of them. Random search is another one. If you're asking about model selection in terms of should we be using a neural network for our problem, or should we maybe use some other model for our problem, a probabilistic model, or maybe a support vector machine, or something like this, yeah, of course, that is also, that is not what we're doing here. Yeah, these are all hyperparameters, yeah. And I guess in practice you would typically have your training set of data, and you could then take a portion of that and put it to one side and use that for validation. So you pick hyperparameters, train a model on the remaining training data, and then look at the separate portion to see how well is my model doing on data that it hasn't seen during training. And in that way, you can then optimize for the hyperparameters. Yeah. But that is, of course, that can be quite a difficult thing in its own. Yeah. Okay, anything else? Otherwise, I'll see you tomorrow afternoon, and we'll talk about training neural networks and regularization. Okay.